sample, what's the difference in the calculations?
Look at that, you're just like pitching softballs for me to just knock it out of the park. That's what we're going to start with.
Cool.
Okay. Other questions?
I was wondering about sampling units. So what is the difference between a sampling unit and a sample?
Sampling unit and a sample, right? So if we're talking about sampling unit, we're talking about like who we're pulling the sample from, right? The sample is the people who we collected. The sampling unit is sort of starts to get into the methodology and how we're going to go through and pull that stuff up. So Howell talks a little bit about some of that stuff, and this is where some of the difficulties between sort of how we're sort of methods and things like that start to get a little bit tricky. You can take whole classes on sampling strategies, and if we're trying to do large representative types of stuff, then that starts to get, if you have an opportunity, there's lots of courses that you can take if you, particularly experimental folks, if you have some extra room to take some stuff. Stat has stuff that looks at methodology and sampling, stuff like that. It's a whole field in and of it to itself. So yeah, go through, make sure that you go through, take a look at that. If you have any questions, just run through and talk. Cool. Yeah, Chris, did you have a question?
No,
okay.
I was interrupted.
Okay, no worries. What were you going to throw in there?
I just said like -1 denominator for.
Oh, for yeah. Okay, cool. Other thing too. Laura, do you want to grab that door? This will not be a huge issue with this set because there's not a lot of interpretations. A lot of what I'm asking you to do is just give me a number, and unless I ask you to tell yourself about that number, you can probably just give me the number. As we move forward, one of the things that's difficult about teaching this class is statistics is more about numbers, and there are ways you can do things that are technically correct that I don't want to take points off, but are kind of a pain regardless. So, for example, if you turn in an assignment with sort of everything's kind of all out of control, and Laura and I have to sit through and spend a couple hours trying to figure out where you put things and piecing things together, it probably won't take points off, but it's aggravating. Same thing if responses and interpretations are kind of cut and paste of some sort of templated thing that's sort of demonstrating less of an ability to think carefully and flexibly about some of this stuff. But at the end of the day, if you give me a technically correct answer, I don't feel it's ethical for me to take points off. But if you go through and you are a big piece of scientific research is organization and being able to communicate things clearly, this is going to be a good opportunity to get some practice with that. And so if we get assignments that are sort of well organized, very clear where things are at, your handwritten sort of calculations and notes are all organized so that you're giving us a favor, interpretations are sort of good and thoughtful and flexible and things along those lines. I'll throw some extra bonus points at my discretion on you if you're making our lives easier, we'll kick you a couple extra bonus points on some of this stuff too. So this may not be something you're concerned about each and every week, but just a nice incentive if you've gone through and put things together so it's easy for us to navigate and go through provide commentary on. So just want to give you a heads up on that. Again, this first one is a lot of just calculating stuff and so some written answers and things along those lines. Again, don't feel like we're necessarily looking for pages and pages on each one of these. Want to make sure that you're kind of getting the points, getting reasonable coverage. If you have any questions about, should I talk more about this, should I talk less about this, just reach out to us, get in touch, we'll sort of provide some guidance there. Okay. So this first set will be due, not this Friday, but next Friday. Plenty of time. This one's not going to be too difficult. The next one, also plenty of time, not going to be too difficult. But then things are going to start cranking up when we're actually using real data. You're going to have to go through and run screenings. Things will be a little bit more ambiguous as they are when we start doing actual empirical work. So just make sure that you're giving yourself plenty of time each and every week to sort of go through and talk with each other and get that going. Okay. Any questions about that? Laura, anything to add?
Rounding?
Oh, rounding issues. Okay. Yeah, Laura put together a question or a thing on rounding. If you're not clear on rounding, We'll go through and post that up. Some of this stuff gets a little bit tricky in terms of the number of significant digits to report certain types of statistics. If I've measured things in whole numbers, reporting a mean to 4 decimal places probably doesn't make a whole lot of sense. That's implying far more precision of your estimate than there actually is. However, we don't want, if you're reporting p-values, you probably need to go more than like odd decimal place for that. I'm going to take what Laura's put together, added some suggestions in terms of making, so how many decimal places in general, just kind of looking for, you know, p-values and different effect sizes, t-tests, things along those lines. But there is some, you know, I can say, oh, you know, generally reported a regression coefficient to a couple of significant digits, right? So maybe 2 decimal places. But if you've got a really low, small coefficient, and it goes 0, the coefficient is 0.004, something like that, then maybe you need to carry that out a little bit. So some of it has to be you being aware of sort of the units and the scaling, and then making decisions in general, right? You think about an effect size coefficient, usually a couple decimal places is sufficient with that. If you carry it out beyond that, you're just basically reporting random digits. That's not useful. So I'll get that out just so you're kind of clear. For me, just in general, rule of thumb for most of the types of things that we're working with, if you're doing hand calculations, if you're kind of rounding things out to 3 decimal places in your hand calculation, that kind of helps me. What ends up happening, you get cumulative rounding error, so your final answer is maybe different than what we have on the key, and then we have to go through and figure out if you made a mistake somewhere, or whether it's just so you were rounding differently and things like that. So we'll try and manage that to the greatest extent possible. There's going to be some of that in there, but just something to be aware as you're going through calculating things. Okay. We'll go on that. Awesome. All right. Cool. So we had left last time a very exciting cliffhanger about differences in the calculation of variance, standard deviation, if we're talking about populations versus if we're talking about samples. All right. So if we're calculating the variance and standard deviation of a population, okay, and what do I mean by a population? What am I talking about with population? TJ?
The entire group of whatever you're looking for.
Yeah, this is everybody. If I have access to all the scores of a population, which will almost never be the case, it might if I'm working in a rat lab and I say these 12 rats are the only, this is the population of rats who have this genetic something or other. But in general, we're thinking about, from a theoretical standpoint, if I'm calculating population variance, here my population includes five observations. I got 5 individuals in this population. What I'm going to do first, calculate a deviation score for each value. What does this deviation score represent, Alicia?
The difference from the mean.
Yep, this is just the distance from the mean, right? Go ahead, like deviation scores are going to come up and up and up and up again. Just thinking about when I'm talking about a deviation score, I'm almost always going to be talking about some difference from a mean value, the distance value, distance from a mean value. So we've got some things that are above the mean, some things are below the mean. Deviation score, just taking this value and subtracting it from the mean, okay? Step 2, we're going to take the square of each one of those deviation scores. Anybody have an idea why we might square that deviation score? Yeah? Go ahead, Leah.
Because it'll get rid of the negatives.
Yeah, why don't we want to get rid of the negatives?
That can mess up the scores.
What's up?
It messes up the scores.
It will mess up the scores tomorrow. You know why it's going to mess up the
It'll
scores?
even out to 0.
Yeah, because what we're going to do then is we're going to sum up those deviation scores. If we just sum the deviation scores, what do we get? 0 every time. If we don't get 0, we've done something incorrectly, right? So we need to get rid of those negatives somewhere. So we're going to take that deviation score, that distance from the mean, and we're going to square it, and then we're going to add those up. This is going to give you your sums of squares. Sum of squares, this is the sum of your squared deviation. That's what a sum of squares is. It's saying if I take all of the deviations from the mean, square those, sum those up, this is your number here, okay? is this a useful value, your sum of squares? Depends on what we mean in terms of useful, right? In general, if we look at our sums of squares and we say, is this a big sum of squares or a little sum of squares? Who knows? I don't know. It's not something that I can look at and have any sort of scaled interpretation of. But this right here, your sum of squares, is just a raw estimate of variability in your data, okay? It's a metric-free, well, it's sort of metric specific to whatever it is that we're calculating, right? But at the end of the day, your sum of squares is a metric of variability, right? It's not going to be comparable to other studies or other measures and things like that, but it's just kind of the raw materials. It's telling you something about the level of variability that you have in your data, okay? Sum of squares comes up a lot. It's sort of the heart and soul of a lot of statistics we'll calculate. On its face, it doesn't have a lot of value, but in terms of calculating our statistical models, it's incredibly important. So anytime you hear someone talking about a sum of squares, in your head you should be thinking, this is just a measure of variability. Not necessarily an easily interpretable measure of variability, but it's just a measure of variability. Same thing as range, same thing as variance, same thing as standard deviation. It's just a different form. Okay? So we've gone through, we've calculated the sum of our squared deviations. And then what we're going to do is we're going to take that sum of squares and we're going to divide it by the number of observations in the population. How many people do we have in the or units do we have in the population? Take that sum of squares. We divide it by the population number here, and what we have is our variance. Our variance is simply the average squared deviation from the mean. Okay, and this is where it starts to become important. A lot of this is okay, fine, whatever. But like, if you're wanting to, once we start to get into more complicated issues, and you're doing diagnostics and trying to think about things, it's very, very important to have a good conceptual understanding of what these metrics mean from a conceptual standpoint, right? And this is why we're going through kind of by definition how you go through and walk through this. Sum of squares, measure of variability, doesn't have a whole lot of interpretive value just looking at it, but it's just a measure of how variable our scores are. Variance, same thing, a different measure of variability derived from your sum of squares. This is just the average squared deviation from the mean. Now, if I go through and I say, Chris, hey, this is the average squared deviation from the mean. Is that something that's super useful for you to interpret?
Not really.
Not really, right? So what we do, or can do if we want to, for our descriptive statistics, we can take that variance estimate and we take the square root of that. We take the square root of that. Now what we have is functionally a measure of the average deviation from the mean. For this population, on average, how far do scores fall from the mean value? Okay, so this is why you'll hear anything that's using this stuff referred to a means-based statistic, because the deviation from the mean is what we're talking about. The mean is the central figure in the calculation of this stuff. Okay, so we've got we've got three measures of variability. We've got sum of squares. It's just the sum of the squared deviations from the mean. It's a measure of variability. It's not super intuitive, but it's just kind of a rough metric. We've got our variance, another measure of variability. This is just in population. This is the average squared deviation from the mean. And then we take our standard deviation, our population standard deviation, take the square root of this. Now we've got something that is actually a little bit more interpretable. We're just saying that this is the average deviation from the mean, or the average difference from the mean in this sample. Okay? Are all scores going to be exactly equal to the standard deviation in terms of their difference? No. But if I had to go through and I had to randomly pull a score out of the population, and I ask you, how far does this score? How much does this score differ from the mean? What's statistically your best guess? Standard deviation. Okay. So if you want to go through calculate a computational formula for your population sum of squares, this is an easier way to go through and calculate that than sort of listing down all your the scores and actually doing it by hand. This is just kind of a shortcut, but they're mathematically equivalent. The reason I want to walk you through this is to start to see really where these numbers are coming from and sort of how we're getting this. Okay. So questions on either sum of squares, variance, or standard deviation?
Just to check
question for standard deviation. Are we going to be labeling it using S, SD, or?
I really don't care in terms of your notation.
For the problem set, S, I'm assuming is equivalent to standard.
Yes, and so in general, in sort of statistical stuff, you'll often see, so in method stuff, you'll see S as the sample standard deviation. In publications, it's usually SD, just because that's an easier way to talk about things. So yeah, I won't get too worried about notation. I'm not going to document once, maybe I'll use it like that. Yeah.
Does this need to be reporting? There is an error, but I just fixed it out.
Oh.
Are we trying to double duty it?
Oh,
There is an error, but I just clicked out of it.
oh,
Do you want me to start it up again, or are you just?
just let it go. Thanks.
That's it.
All right. Yeah, that's all right. This is the most important part of the lecture, the standard deviation. That's sort of the correct. You can watch it and be like, I don't know what's going on. This is the most important piece. Okay, so we're going through, but this is one of the things that you should be thinking about all the time in the back of your head. So I've gone through and I've calculated some statistical value. First thing you should be thinking in your head is this a reasonable value? Okay. If these are my scores, right? And I go through and I'm looking at my scores and I say the mean here is 6. The difference between the closest score and the farthest score is somewhere between 1 unit and 5 units away. Where should your standard deviation fall?
Between those?
Yeah, between 1 and 5, right? If you get a standard deviation of 10, is that a reasonable statistic? No, not a reasonable statistic. If you report that, this is what I'll be doing in my head at you. Always, if you're going to be calculating something, look at it and say, does this make sense? Right? I've calculated a t-statistic that's not significant. My t-value is 35. That doesn't make any sense, right? I've got an effect size, and this might not make sense to you right now, we haven't got into it, but I've got a correlation of 2, right? Does that make sense? No. So one of the benefits of knowing conceptually what's going on when you're going through and calculating this stuff is that you can go through, take a look at it after you've made your calculations and say, given what I know about these data, does this make sense or does it not? When we're learning new statistical methods and doing things that you're not familiar with, a lot of times you're going to come up with numbers. One of the best ways to know whether or not you're on the right track, ask yourself, does this make sense? Okay. So that's how we would go through, calculate variance, standard deviation, if we're working with a population of scores. Okay. Now the goal of our inferential statistics is, remember, that we don't have access to the population. We can't get the whole population. If we got the whole population, we wouldn't need to do statistics. If I was interested if population A was bigger than population B, I would just measure the score for population A, I'd measure the score for population B, and I'd see if they're the exact same value. And if they're not, then I say, nope, they're different, right? But we can't do that. We can't get those scores. So what we need to do is we need to calculate statistics based on samples and use that to infer something about the corresponding population parameters, okay? This whole process based on the assumption that our samples are representative, okay? This is very, very important. I thought I underlined this at some point. Okay, well, yes I did, but I meant to, because it's very important. So, one thing we need to be making sure, should always be when we're looking and evaluating our statistical models, is trying to make sort of in the back. You guys are all in David's methods class, right? Right now? We'll be taking methods next semester. Okay. There's a lot of stuff that the methods, the statistics go hand in hand. You can't just look at statistics and make a reasonable inference about anything. You have to be thinking closely and carefully about the methods. But sort of all of this thing that we're doing with our inferential statistics is we've assumed that our samples are representative of the population at large. The problem is that our samples consistently underestimate the variability in the population, okay? If we go through and we take a look at, this is the distribution here, I go through and I collect a random sample. It's a very good sample. It's a representative sample. I'm engaged in the gold standard sampling, and it really is a true representative random sample. Where's my sample going to come from predominantly? Right here in the center, okay? What are we missing right here in the center, Nick?
The outliers.
Yeah, the stuff, right? The things that are on the really, really high end, the really, really low end. And so we're trying to measure. If we're capturing the mean, do we have a problem with the mean? If we're using the sample to calculate the mean? No, why not? Why are we worried about the mean?
Because when an outlier is, they're kind of outside of the mean.
Yeah, right? We calculate the average of this and the average of this, we still get the same value, right? So our mean isn't biased. The problem is our measure of variability start to get biased because we're not in a sample, particularly in small samples. Our chances of grabbing someone who's 8 feet tall and someone who's 3 feet tall are probably next to 0, right? And so what we're going to do is we're going to systematically, if we are just using the formulas that we use to calculate population variability, when we're using samples, we're going to systematically underestimate the variability of our samples, okay? So we need to do something different because we've got a biased statistic. We say our sample statistic is biased if our average value systematically overestimates or underestimates our corresponding population parameter. If based on our calculation, our statistic is systematically bigger or smaller across replications, we're going to say that this is unbiased. If our, on average, we're not saying any individual parameter or statistic we get is going to sort of be above or below to some extent. But on average, if we're systematically higher or lower, we're talking about bias. If the average value of the statistic is equal to the population parameter, this is our unbiased statistic, right? And as you start to move forward with methodological research, you'll hear people talk about, well, this is a biased estimate of this parameter or something along those lines. This is what it's talking about. It's talking about over an infinite number of replications, this sample statistic does not converge to the actual population parameter, right? And so we know that if we go through and we calculate variability based on our population formula, we're going to have systematic bias. And what's the bias going to look like? How is our statistic going to relate to the actual population parameter if we're talking about variability? It's going to be lower. It's going to underestimate. I'm going to say that there's less variability in the population than there actually is. Fortunately, slight modification goes through and corrects this. Okay. All we have to do, and people smarter than me have figured this out. I'm not sure exactly the proof. This is one difference between what we're going to do. So, anytime you're sort of feeling aggravated at me about me making you do calculations, I'm not making you do any proofs or anything like that. I have a buddy over in econ, the econometrics, and so like you don't need to prove the normal curve to me in this class. It's not a big deal. So we're applied people. We'll trust the people who've got this worked out. But if we want to go through and calculate an unbiased estimate of the population variance based on our sample, what we need to do is we just, for calculating our variance, we take the sum of squares, same way we always calculated sum of squares, and we just divide that by that n minus 1. So just whatever our sample is, subtract 1, okay? Dividing by n minus 1 reduces the denominator, resulting in a larger estimation of the variance, okay? Why?
Because you're dividing by less.
Yes, on account of math, right? Because that's how it works. Like 90%, 73% of what we will be doing in this class when you're working with statistics is a basis of ratios, right? And so understanding what happens if something gets larger or smaller is really, really going to be helpful in terms of conceptually understanding what's going on. Problem is if we just use our population estimate, this is too small, right? But if we take the same thing, holding all things equal, and divide that thing by a smaller number, what's our outcome going to do? It's going to increase, it's going to adjust, right? And is our adjustment going to be bigger or smaller? Are we going to get a bigger adjustment or a smaller adjustment with small samples relative to large samples? Go for it. Bigger, yeah. If my sample is 10, and I take a number and divide it by 10 as opposed to, if I divide it by 9 as opposed to 10, I'm gonna get a sizable adjustment. If this is 1,000 and I divide by 1,000 versus 999, it's gonna be much less of an adjustment. Why does this make sense given the problem that we have with underestimation of the population variance? Yeah, Chris.
So with the larger sample size, you're assuming that you're collecting more of the population.
Beautiful. If I've got a sample size of 1,000, I'm much more likely to catch those extremes. That's a really big sample. I'm much more likely to get out on the edges, and so probably my sample or my sample value, my test statistic is going to be less biased than if I've got a sample of 15, right? If I go out on campus and I grab the first 15 people, walking through crises, and use that as an estimate of variability of height in campus, I'm going to be way, way low on that, right? But if I go through and I grab 250 people coming through campus, I'm going to get very small people, I'm going to get sort of athletes and basketball players. It's going to give me a better sense, right? And so conceptually, you can start to see how this works. It's a very, very small adjustment, but that adjustment is dependent on the magnitude of the adjustment. Is depending on the size of my sample. As my size of my sample gets larger and larger, I get less and less worried about bias. When I have very small samples is when this starts to become a problem. Okay. So, same set of data. Again, first you're going to calculate our deviation score. We're going to square those deviation scores. We're going to go through some of the deviation scores. Everything to this point, exactly the same. No difference here. But then when we go through and we calculate our sample variance, we're just going to take our sum of squares divided by n minus 1. In this case, it's going to be 4 instead of 5. Is this going to result in a relatively big or relatively small adjustment to my opinion? Relatively big adjustment, right? So it's going to make our this estimate much larger than it was, at least noticeably larger than it was if we were using the population estimate. Then we just take the square root of our variance, gives us our standard deviation, our sample standard deviation. But again, only thing that's differing here is the denominator that we're using for our variance versus our standard deviation. Okay. So this is why when we're talking about are we ever really using a population formula for calculating anything that we calculate? No, right? And so when I talk about interpreting your standard deviation as approximately the average deviation from the mean, this is where that approximately comes in, because it's not technically exactly the average deviation from the mean. Average deviation from the mean would be if we're using population formula. Here, it's close to the average. It'll be closer to the average if you've got bigger samples versus smaller samples. But just conceptually, it's fine to think about your standard deviation as sort of roughly the average difference from any randomly selected score from the mean, or the average difference between two randomly selected scores, or the average error of any individual measurement from so your point estimate of the mean, things along those lines. It's just not exactly the same because of the adjustment that we make here. Yeah.
So step by step, it says population standard deviation. Should it be simple standard deviation?
Oh, yes, that should be. Thank you. Laura, can you shoot me an email to remind me? Yeah, thank you. Excellent
I
catch.
had an issue with it in the problem set, so I was like,
Oh,
I
okay.
did the population standard deviation, and I was like, oh, this is wrong.
Okay, thank you. Yeah. Bonus points for paying attention. All right. Any other questions with this stuff? All right. Cool. So we go through, do a quick table, and this is just a small example. Five observations. We see our population sum of squares, sample sum of squares is the same, but we see our variance is systematically larger if we're calculating using our sample formula versus our population formula. Standard deviation, same thing. Our sample formula is producing a larger estimate than the population. These are just your basic formula here. You don't need to worry about memorizing formula. No one's going to put a gun to your head and sort of have you crank out the formula for sum of squares in your lifetime. This is a statistics action movie. It's like Bruce Willis and it's pretty cool. But it's not going to happen. You're always going to have access to go through a table. So don't spend your time trying to memorize formula for exams. Focus on conceptually. So what does this mean? So what are the influences? Things along those lines. Okay. Cool. All right, so our standard deviation is nice from a descriptive standpoint because it's talking about, it's giving us an index of variability, measuring sort of a typical distance from the mean. Not technically the average, but if we've got reasonably sized samples, about telling us about how far the average person is going to fall from the center. In any distribution, some people are going to be close, some people can be far away, but it's just a nice conceptual way to think about how spread out scores are. And if we know both the mean and the standard deviation, it's going to give us information on kind of the distribution of scores, information on where some randomly selected score is likely to occur, some sort of inference about individual scores, right? So if I can go through and use looking at a normal curve, right? If I know anything that's follows some sort of standard, normal distribution, right? I know if we're anywhere between a standard deviation above, standard deviation below the mean. If we're talking about something that has a normal distribution, I'm going to say that's about 2/3, a little over 2/3 of the sample or the population is probably going to fall within the standard deviation above or below, right? If we spread it out, about 95% of the observation is going to fall between 2 standard deviations above, below, or below. If we go out 3 standard deviations, we're talking about 99% of the population of the sample should be, if it's following the normal distribution, we're expecting to fall between 3 standard deviations. So this starts to give us a better sense for, if we know what the mean and standard deviation of this sample or population is, starts to give us a better sense for where any individual score is likely to fall. Okay. So we're thinking about, say the mean height of adult males, 5'10" with a standard deviation of 3, right? These are population parameters that I semi-made up and we think that we know, right? If we have someone who's 5'6", is that person, so what can we infer about that person's height relative to sort of the population as a whole? It's going to be below the mean, yeah. By how much? I mean, are we shocked to find a grown man who's 5'6"? Not really. I mean, it's a little above it, a little more than a standard deviation below the mean, right? Standard deviation below is about 5'7", so we're just so I mean, this person is objectively shorter than the average person, but they're probably not hugely short, right? What if we find someone who's 6'6"? Yeah, where are we at there in terms of the person? Yeah, over 2 standard deviations, and we're getting above 2 standard deviations. That's a score that's starting to get pretty extreme. Someone who's 5'2", yeah. How many standard deviations below are we there? Yeah, right. So we can go through, if we know something about the mean, the standard deviation, we can start to make objective qualifications on how extreme is this relative to their sort of other people in the population, the distribution, which starts to become super helpful, right? And we don't do this enough, right? We just, in our statistics, we're looking through like, oh, yeah, this is the score, blah, blah, blah. For you clinical folks, if you're ever on my clinical team, you try and give me like a BDI score or something like that, that's like, oh, this is the number. I tell you, that's just, I don't know what that number means. This is, you can put in any number you want, so that give me some sort of sense for distribution or something like that, so I know sort of where this person is relative to what we might expect within a clinical setting, right? Same thing, we can do the same exercise with, say, extroversion scores here, right? If we've got a measure with a population mean of 85, standard deviation of 20. Here, you know, we've got something that's getting close to 2 standard deviations above the mean, right? So that's a pretty high level of extroversion. This is even higher, that's pretty low. We can start to go through and sort of draw meaningful inference about these scores if we know something about the population parameters. So, again, if we're thinking about how we go through and use this in terms of developing inference, our goal is to try and go through and separate signal from noise, right? We want to see, are the things that we're seeing, are the data that we're, or the patterns that we're seeing, is this actually something that's reflective of a population thing, or is this just random fluctuations, right? If we're talking about data that's fairly easy, or if we're talking about data that has relatively low variability, right, everything's kind of close, it's sometimes pretty easy to see patterns. If we've got data that has high levels of variability, much more difficult to see patterns within the data. There's more static going on there, right? So if I give you these two groups, we've got experiment A and experiment B, which one of these is it easier to see systematic differences between groups A and B? Why do you say that?
They're usually like closer, they're grouped closer together.
Within the groups, yeah.
In each group.
Yeah, and so who's scoring higher than who? Group 1 or Group 2?
Group 2 is scoring higher.
Group 2 is scoring higher than Group 1, but it's easier to see this in Experiment A because all the scores are kind of close together. Experiment B, you've got much more variability within our groups, right? People are kind of all over the place, so it makes it much more difficult to try and get a sense for, okay, like, so where are people at? Who's scoring higher than who? Right? People see kind of how we're starts to get difficult, and so we can start to think about this in terms of variability as creating, at least with group-based comparisons, a lot of background noise, right? It's getting hard to see sort of who's sort of outperforming who. If we go through and take a look graphically, and again, this is why a lot of graphical methods are really, really nice for sort of demonstrating kind of what's going on. We use just a simple bar graph here. If this is group for experiment A, this is group 1, this is group 2. Is there any question on who's doing better or outperforming who? It's pretty obvious, right? If we go through and take a look at the high variability, it's much more difficult to see, right? The average difference in the group is the same in both cases. It's just group B has much greater levels of variability in the data, and because of that, it's much, much harder to detect this pattern. Okay. What types of things might impact sort of variability in this hypothetical study? Yeah.
Sample size.
Sample size, that can do it, right? What else? Sample selection, maybe. What's other stuff that adds noise to our data? What do you think, Tony?
The measuring.
Yeah, the measure, right? If I use a measure that's kind of all over the place, right? It's not internally consistent. It's not not especially reliable in terms of test retest stuff. I can give exactly the same test every day for a week, and the scores bouncing around all over the place on something that shouldn't bounce around all over the place. That's adding fuzz to the data, right? What about if I have really good, well-trained RAs who are on top of their protocol versus people who are just kind of shooting from the hip on stuff, right? These are the types of things, these are the methods that actually has a real practical impact on our statistical analyses, right? We want to do statistics over here, talk about methods over here, but they run hand in hand. If I've got a junk protocol and I'm not keeping a tight reins on my RAs, and I'm using measures that aren't super well validated or reliable, this is the type of stuff that we're getting, right? So even though I've got the same difference between each group, I've got a whole bunch of within group variability that's causing a lot of static. It makes it much, much harder for me to detect that difference that I've hypothesized. And so wanted to be very, very careful about how we want to do this stuff. Okay. Questions on this? Okay. So if we're talking about characteristics of standard deviation, we talked about characteristics of our mean values or measures of central tendency. If we're talking about our standard deviation, adding or subtracting a constant from each score in a distribution doesn't change the standard deviation, right? Why not? Yeah.
You're doing it from each score.
Yeah, it's just shifting it around. So here's the thing, it's just shifting that distribution around. So the standard deviation doesn't change. I can add 10 points to every score in the distribution. Is that going to change my mean? Yep, it'll change the mean. It'll increase the mean by 10 points, but it's not going to change my standard deviation at all, right? But if I go through and I multiply or divide each score in a distribution by a constant, then I'm going to see a change in the standard deviation by that same constant. I'm measuring something in inches, and I have a standard deviation of 12, and I decide to convert that measure to feet, what's my standard deviation going to be? 1, right? So again, it's just a scaling issue, but this starts to become important later on. If you're doing like structural equation modeling types of things, you can run into data that are ill-scaled. And so maybe I'm sort of looking at the regression of this one measure that has a 0 to 1 scale and another one that has a 0 to 1,000 scale. The variances on those are going to be massively different, and so one of the things can cause problems with your model. So one of the things you can do to address ill-scaled data is go through and say, all right, I'm going to multiply the 0 to 1 scale by 10 or 100 or whatever it does that kind of brings it in line, and I'm going to divide my 0 to 1,000 scale by some factor to kind of bring those in. It doesn't change the measurement, it doesn't change the distribution, but if we're worried about comparability in terms of our variances, this is something we can make use of. So factors that are going to influence our variability, extreme scores, range, variance, standard deviation, all influenced by extreme values, okay? Which ones are extreme, which one of these variability statistics is extreme scores going to be the most problematic with? Okay, yeah, but if we're talking about range, variance, and standard deviation, which one of these measures is going to be most impacted by really extreme scores, CJ?
Right.
Yeah, the range, right? As my sample starts to get bigger and bigger and bigger, if I have a hairball case that's way out there, it's going to impact my variance, but probably not a ton. But it's always going to impact my range. It doesn't matter if I have a sample of 10 or a billion, that far scale is still the far scale, always going to impact the range there. So sample size, our range increases with sample size. Why does our range increase with sample size? What do you think, Alicia?
Because you're going to have more numbers.
More opportunity to get those ends, right? We see though that our variance and our standard deviation remain relatively stable, right? Because we've gone through, we've made that adjustment. As our sample size gets bigger and bigger and bigger, we're getting closer and closer and closer to capturing the full population, even though it's maybe not even close, but it's getting bigger and bigger and representative. So we see that our variance and our standard deviation are going to remain relatively stable. The range is going to get bigger with large samples. Stability under sampling, range can jump around unpredictably, right? My upper limit and my lower limit that are the 2 scores. So my range is dependent on 2 scores. The highest value and the lowest value. Across multiple replications, from sample to sample, that can jump around quite a large bit. Our variance and our standard deviation continues to be pretty consistent. But the problem is, if I have an open-ended distribution, if I have those censored data, right, where I have miles driven 0 to my top category is 100 or more, I can't calculate variance or standard deviation there. I need to have the actual value, but I can calculate. I can't calculate range. Actually, I could say from the top of this down. But so this is one of these things we want to be careful. Mistakes that we can make, or errors that we can make when we're setting up our studies, and like, oh well, I'll just say this or above. Well, you do that, but then what you run into the problem with is having a hard time meaningfully calculating stuff. Okay. Questions on any of this? Cool. All right. So we've got our distribution shapes, our normal distribution here. Normal distribution, mean, median, mode, all the same. Sort of a nice symmetrical normal distribution here. Everybody's familiar with the normal distribution, we all like it. But we can also have symmetrical distributions that are not normal, right? If we're talking about a symmetrical distribution, we can just take it, we can fold it in half, we can make construction paper, snowflake out of it, sort of do some stuff, but it just means we can go through, fold it in half, it's going to be the same no matter what, but just because a distribution is symmetrical doesn't mean it's normal. You can also have symmetrical distributions that look like this, right? Anybody know what do we call this? It's fancy, man. It's hard. What's it called? So someone's
Like kurtosis.
yeah, kurtosis is a problem. Someone was whispering it. Be proud in your answer whether it's right or wrong.
This is a square distribution. I don't even know how they come up with these names with statistics sometimes, but this is a square distribution. It's symmetrical, right? But it's not normal, okay? And we would have positive or negative kurtosis on this.
It would be bad.
It wouldn't be great. Yeah. There are worse types of things. So, all right, we'll save that for down the road. But so this is, and we're talking about the shape of distributions, talking about sort of what they're looking like, right? I can calculate mean, standard deviation, variance for any distribution, but I actually, knowing the mean and the standard deviation of a distribution doesn't tell me a whole lot about the shape, right? So what we're going to do is we're going to skip into things like skew, okay? Skew, you'll hear this described as a third population moment, a third characteristic of a distribution, describes the symmetry of that distribution. Positive skew has a tail extending out towards upper end, negative skew, tail extending out towards the lower end. As we talked about before with this, if we have a skew distribution, if it has a notable skew, and again, this all exists on a continuum, but if it's too much, what ends up happening is that our mean isn't any longer a valid index of central tendency. What we'll end up having is that our mean is going to be drug out farthest towards the tail, our mode is going to be back towards sort of the hump of the distribution, and our median is going to be right in between not necessarily right in between, but the median is going to fall between the mode and the mean. And so this is why with seriously skewed distributions, the median stuff is probably going to be the best. So Nick, if you're working with alcohol and substance use stuff, a lot of that is going to be horribly skewed. I would imagine in your literature, you maybe see people referring to medians often, right? Tamara, what do you do? ADHD types of stuff, right? So aggressive types of behaviors, the same type of thing. This is probably going to fall sort of median-based stuff. Anybody do like reaction time work or anything like that? Reaction time stuff. CJ, what are your interests again?
Anger about group studies.
What's that? Oh, anger about group stuff. Okay. We were doing reaction times to sort of how you respond to whether or not you like in groups or out groups or things like that. Any type of reaction time data, hugely skewed, right? Most of the time we're on top, really doing things quickly. Sometimes you get a delay drawing things out. And so what we need to be doing is thinking about to what extent is this data skewed and asymmetrical, and does that then start to impact how we're thinking about measures of central tendency. Our kurtosis, this is our fourth population moment. Kurtosis is talking about the shoulders or the peak of the distribution. So our positive kurtosis, it's leptokurtic. You can talk about things as leptokurtic if you want to be fancy, or you don't. You can just talk about positive kurtosis. I don't care however you want to do it. But what we've got here is a distribution with heavier tails and a narrow peak. Okay? What's a classic leptokurtic distribution? Think about your t-distribution relative to a normal distribution. A nice sort of normal curve. T-distribution, the problem with t-distribution is they have positive kurtosis. It's kind of peaked at the top, and then the sort of tails kind of flatten out as you go outward. Negative kurtosis, this is good. We've heard this as platykurtic distribution with a flattened center, heavy shoulders, kind of a dome-shaped distribution here. Okay, and so the problem is that kurtotic distributions tend to, doesn't matter whether they're positive, whether they're negative, kurtotic distributions underestimate the population variance. So if I've got a sample and it's horribly kurtotic, my primary concern is that it's underestimated the actual population variance. Okay? Why are both of these result producing underestimation of your variance?
So you're not getting the full range of what your population would supposedly represent.
Right. So here, particularly, you're not getting the full range. How is our positive kurtosis underestimating the variance, because we're getting those.
It's heavily skewed to like the median.
Okay. Not, I wouldn't say skewed, not skewed, but it's bunched up around it,
Yeah.
right? So all of this stuff in here, which is, we're underestimating all this variability here. We're picking up some stuff on the tails, but all this stuff, where the bulkier distribution is, we've underestimated that, because all those scores are too close together. So the primary concern with having a very kurtotic distribution is that we don't have, potentially underestimated the variability of our data, or the population, as population scores. So it impacts our quality of variance tests, contributes to some biases and parameter estimates, standard errors, depending on what type of analyses that we're doing. Now when we get into some stuff in bigger samples, we start to become less and less worried about some of this, but it's one of these things we need to be careful about and sort of thinking about. Questions about skew kurtosis? Okay. Very kurtotic, right? This is our negative kurtosis. A square distribution would be primary example of just a distribution having very negative kurtosis. When we're going through, we're running data, if we go through and we see a negative kurtosis value, this is probably about what you should be thinking. It's probably going to look like something along these lines. Okay. So, we're thinking about statistical indices of skew and kurtosis. All right. We can go through and run a formal statistical test for skew and kurtosis. Okay. And this will tell us whether or not we have statistically significant skew and statistically significant kurtosis. Why might we be not overly concerned whether or not we have statistically significant skew or statistically significant kurtosis? Seems like it should be a big deal. Right, I've got significant skew. Yikes! Why might that not maybe sound like more of a big deal than it actually is?
Because you're expecting that, depending on the population you're looking at.
Okay.
I don't know.
So if I'm expecting it, right, you know, if I, again, look at cocaine use in undergrads in terms of sort of, you know, days of use or something like that, then I'm expecting that to be pretty skewed data. And if it comes out to be significantly skewed, I'm not super surprised about it. So that's a consideration. Statistically, from a standpoint of our models, why might we not be overly worried about having statistically significant skew? What does it mean if I have statistically significant skew? Sounds like it sounds like I have bad levels of skew. But what does anytime I say anything is statistically significant? What does that mean? Not any time, but like sort of 90% of the time.
If you're going to do this again 98% of the time, this would be skewed.
Okay. I'm glad you said that. We'll work on that. But that might be something that people would go through and say, but not quite in terms of this. What does it mean if I have a statistically significant difference? What does that mean? Almost all the time. Some value doesn't equal what? What do you think? Sally? Yeah. 0.00 off into infinity, right?
Yeah.
The sum value doesn't equal 0, right? The sum difference doesn't equal 0, the sum coefficient doesn't equal 0. If I say something statistically significant, all that means based on our data, we're sort of saying it's unlikely that this thing is actually 0 in the population. Are the assumptions of my statistical analyses that my skew and kurtosis is exactly 0? No, right? Because then that wouldn't be realistic. I could know you couldn't do anything anytime, right? So if I see a test that says my data have significant skew p less than 0.001, that just says that, well, based on my data, that the skew value is not 0. But the assumption of my test isn't that the skew value is 0, so I don't really care about it, right? And what happens if I have a sample of, say, 500 people? What's that going to do to the power of my test? Going to jack it way up, right? And this is what happens. Sometimes we review a paper and we found significant skew, so we did all this crazy transformation of the data. Like, what's your actual skew in your sample of 300? It's a skew of like 0.25 or something like that. Like, you didn't need to go through and do a bunch of stuff to your skew because you have significant skew you just made your data all like horribly difficult to interpret by correcting a problem that didn't need to be corrected, right? And particularly if we're using large samples, you're always going to get statistically significant skew kurtosis because your data are never going to be perfectly normal. That's fine, we're not worried about that because no one expects your data to be perfectly normal anyway. So we've got to be careful when we're thinking carefully about what our statistical tests tell us, and not sort of freaking out because we have a statistically significant something or other, okay? So what we do, and so what we're always going to do is ignore those skew and kurtosis significance tests because we don't care about those. What we're going to focus on is looking at the absolute values of skew and kurtosis. Okay? And if we're looking at values of skew and kurtosis values less than or equal to 2 often uses like a rule of thumb for something that's not a non-problematic violation of normality. Okay, so if we've got, say, a skew of 1.5, that doesn't mean that our data are normal, that they're approximating normality. If you see a data set, if you see a sample or distribution with a skew of 1.5, it's going to look pretty skewed, right? But we're using this as a general rule of thumb, particularly if we've got reasonably large samples, as something that's not maybe a problem or something that we need to go through and start thinking about transforming or doing a bunch of things like that. Same thing with kurtosis values. A neutral kurtosis actually has a value of 3. So, Alicia, when you're using this data, it'll give your kurtosis values where 3 is your sort of neutral point. SPSS will go through and subtract 3 from the kurtosis value. So if you have neutral kurtosis, you don't have any, your data is not kurtotic at all, you get a value of 0, which is kind of nicer, easy to look at, but also subtracting 3 from things isn't hard. So, but in general, anything that's, if we're looking at things that are less than 2, we're saying, oh, okay, that's probably reasonable. But remember that this violation exists on a continuum, and it's dependent on a lot of things. If I have a skew of 1.5 and I've got a sample of 300, am I going to be too worried about that? Probably not. If I got a skew of 1.95, I've got a sample of 20 people, am I going to be worried about that? Maybe a little bit more, right? Depending on what type of analysis I'm doing. What I don't want you to do is use these as a bright line benchmark. We're doing absolutely 100% against bright line benchmarks. A skew value of 1.99 is not meaningfully different than 2.1. We will not treat, like, this is one thing you'll be fired up. Like, do not use these and you sort of think about these as different things, right? And so wanting to take this into consideration with other stuff as sort of, is this problematic, is this not? And then going through providing recommendations for what do we do with this moving forward? Is it something that needs transformed or not? Being careful taking in a bunch of different information here. If we're talking about big sample stuff, you know, there's some SEM literature suggesting that skew less than 2, kurtosis less than 8 might be considered as non-problematic. Not large enough samples, but fine. And the text is probably pushing it a little bit. The one thing that I want you to do, and so this is something I've changed this semester, what we don't want to be doing is talking about these data as it's approximately normal because skew and kurtosis values are less than 2. If you say that and then you actually look at the distribution, it's going to be very clear that it's not normal or approximating normality. We're just talking about this as a violation or a deviation from normality that may not be something to get too worked up about. Questions on thinking about this stuff? Okay. Again, when you do this in my head, is what I'm doing, right? Think about bright line benchmarks, and I can tell you what this was supposed to do. Again, as we start to get larger and larger samples, we get less and less concerned about kurtosis. Again, remember our primary concern with kurtosis is underestimation of the population variance. And so as our samples get about 100-ish, we get less concerned about positive kurtosis, negative kurtosis. We get samples exceeding 200. Less and less worried about, so maybe some more severe violations of kurtosis. Again, this has to do with variability and the extent to which we've underestimated something. concern, I made some changes to this, let's go through and take an early break. Go ahead and take sort of 10, we'll jump back in when we get down, and you can go down through and make sure that I've got the right slides, because I went through and changed some stuff, making sure we're on the same page with things. Every time I plug in this flash drive, it tells me there's a problem with it, it's corrupt, and so I'm just waiting for all it to kind of fall apart. So this is good. I got the right slides, so now I'm not surprised that things like are popping up. That's not a good place to be in if you're trying to lecture or do anything. But questions on sort of where we're at up to this point with any of this stuff. A lot of this is review, but it's good to get, I just want people to be solid on this and feeling comfortable as we move forward with things. Yeah?
Should be a lowercase n for both of those.
For both of those? I guess I'm not going to get too worried about. Oh, are you? Okay. Like, you're on a roll. I'll give you the one mistake. Yeah, yeah. It could very easily be that for populations greater than or equal to. Cool. All right. Feeling good? All right. Cool. And then I'm sort of giving you an eyeball side eye there. Let's jump into outliers. Okay. Outliers, extreme values for a given variable, and this is what you want to go through to start pitching outliers and things like that. It's very, very important to think about and sort of take a look at your data feel and figure out like what's going on, like why is this value an outlier? Before I go throw anything out of my data, I need to go through, do some detective work. Very, very possible that it's an incorrect data entry, right? If we're going through and entering things, someone added an extra 0 or an extra 1 or something, and now all of a sudden it's out of bounds. Always want to go back through and make sure that you've got in your research a hard copy of your physical file, be able to go through and say, so what's going on with this? This is having to do self-report stuff. Sometimes, it's a 0 or a 1 to 5 scale, and a respondent will write in a 6. We can't have the 6 isn't part of the scale, right? So you want to go back to be able to check that. Be able to specify a missing data code in SPSS. What I'll encourage you to do, and what I do a lot, if a value is just missing, and then I pull it up, I don't know if it's missing because we didn't have the data or because an RA skipped that item or what. And so what I'll do is go through in SPSS and put a 999 code, because 999 isn't a valid response to anything. That's a placeholder saying this is a missing, indicating a missing value for this scale. But if I don't tell SPSS that 999 equals missing data, it throws things out of the loop, right? So making sure that you have that specified in the system. Case is not a member of the intended population of study. Sometimes we get outliers because we've captured someone who's not part of the people who we want to study, right? So let's say I'm looking at income among undergraduates, freshmen or something like that, and I find someone who's reporting an income of, $150,000 a year, and I'm like, yikes! This is like maybe an executive who's just taking, there's a business person who has their own career, they're just taking this as the thing. But this isn't the person who I'm trying to look at, so I'm fine excluding them from my analysis because they're not part of the intended study. But I will want to go back through and verify that in my data. Case numbers are a number of the intended population, but population variability underestimated by a sample, right? So if I'm going through and looking at, say, age of my intro students, right? And I'm interested in all intro students, and I get someone who is advanced age in Psych 1000, which could happen, right? Now this person isn't necessarily not a member of the intended population. My population is all people taking Gen Psych students, and there's plenty of people coming back to school later in life to go through and take some stuff. But my one sample might not have captured it, and so even though it is, I don't have a great range of variability, and so I've captured somebody on the edge, then I need to go through and figure out sort of exactly how we do this. If I'm looking again, you picking on Nick, but it's just the thing that it goes. So if I'm interested in substance use, I get someone who's way out there, and I got a sample of 30 because there's not that many people, say, using opiates or in my sample or something like that. But I've got someone who's using a lot of opiates. I don't want to throw them out because the person I'm interested in. It's just I don't have a big sample to sort of catch that tail. So always wanting to be not just identifying your outlier, but trying to get a sense for what's going on, how do we understand this. If we don't address outliers, possible consequences, undue influence on our coefficients, right? Sort of dragging things around one way or the other. We can have inflation of type 1 and type 2 errors, problems with generalizability, right? But again, like anything else, this all depends on context. If I've got an outlier in a very, very large sample, probably less of an issue than I have a massive outlier in a very small sample, right? So all of this stuff needing to be taken into account. So there's no hard and fast rules like, oh, this is the level at which we pitch people and throw people out, okay? So generally thinking about this in terms of our continuous distributions. Also important to remember that we can have outliers in our categorical data, particularly with our dichotomous data, sort of our 0-1 variables. If we had hugely unequal splits, say like 9-1, functionally what this ends up being is this variable is representative of a univariate outlier. What do we end up happening if I've got, so example here, let's say I want to have, look at sort of minority status in some study I'm doing, and I've got 304 people who identify as white, non-Hispanic, and 22 individuals identifying as racial as a minority. That's hard to look at, right? People, any individual in this category having a much, much stronger influence on sort of the outcome than any one individual in the larger category. We start to see attenuation of our associations with these types of things. The correlations that we might expect, or the association we might expect, systematically smaller than it is in the population. And so unless this is something that's essential to your analyses, and you should have thought about this before you collected the data, thinking about omitting this stuff, because I can't smooth or transform or do anything with this. I need to be, if you're looking at doing research with something that is a potential low-level occurrence, you need to be thinking about, am I going to be able to capture enough people in this area to be able to make sure that I'm doing anything with this, right? Ryan, my senior student, is doing some work looking at suicidal IDs. He's really an agent of the Pepper Lab at this point, sort of spying on on all our super top secret stuff. But thinking about suicide attempts, right? Now, if I get a large enough sample, I'm going to get suicide attempts, but I can't say, oh, I'm going to grab a sample of 30 people and have enough people with suicide attempts to just run some analyses or something like that, right? So we're needing to make sure we're looking at this carefully, planning beforehand. Questions about outliers in terms of like when we're thinking about categorical data. And this can happen too if you have things that are like 3 levels, right? So say you want to look at at least something to do with veteran status, right? And you have student civilians, you've got former military and active military, and you've got, 10 former service members and 2 active service members and 300 civilian students. It starts to become hard to know how to go through and do that. So a lot of this ends up being methods in planning your study and thinking about, can I actually capture the demographic I'm looking for with this. Okay. So for our continuous data, we think about outliers as operationalized as those with extreme standard scores. Standardized scores, we're going to talk about this in just a few minutes, but if we have a z-value or a z-score greater than, greater than or equal to plus or minus 3.29, this is associated with the probability value of less than 0.001. Oftentimes this is a means of saying, okay, here's sort of our cut point for being a potential outlier. What we can do, we're going through screening our data, we can go through create a standardized score and sort of basically say how many standard deviation units are away from the mean. Is this variable kind of use that as a general rule of thumb? But one, always wanting to use some sort of graphical method to see sort of what this looks like. So I find 3 cases that exceed a z-score of 3.29. What are these looking like? Are these scores that are sort of here's sort of the last end of the top end of my distribution, then I got a massive gap, and then these people are hanging out? Maybe you have a stronger argument for that as an outlier. if this is a skewed distribution and somewhere along that continuous distribution, now all of a sudden someone tips over from a 3.28 to a 3.29, I necessarily want to identify that as an outlier, or maybe it's an extreme score, right? And again, so I want to prefer extreme scores to outliers. Outliers make it sound like sort of something's way out there. This is talking about extreme scores. Perhaps if I've got a large sample, I'm almost always going to get extreme scores. If I don't have, if I have a sample of 200, 300, and I don't have some extreme scores in there, something wrong happened, right? And so wanting to be very, very careful and not just going through and saying, oh, if it's on this side of the line, it's not an outlier. If it's on this side of the line, it is. Again, wanting to take in this context what I'm studying, right? So I might expect to find some outliers. If I don't find some outliers, that's weird, right? I want to think about how much it is, how extreme is this a part of the continuous distribution. All these things are going to start, what type of analyses I'm running. All these are going to start to plan on how I deal with sort of what's going on, but always want to graph this a couple of different ways to try and get a sense for the magnitude of the outlier and how it relates to, or the extreme case and how it relates to other values in the set. Okay. Questions about outliers? And again, a lot of times we're going to leave outliers in. I mean, unless they're very clearly going to be problematic in a way, right? We start cutting our data out and sort of only using the people who just do exactly what we want to do. We have the potential to bias things in a pretty serious way. Now, if it's way out of bounds, that's one issue. But again, as I mentioned before, for the types of the research that we do and the types of measurements that we collect, it's hard to get someone who's going to be a super huge outlier, right? I drop Bill Gates in any sort of econ, sort of income-based study. He's going to be a way, you got to get rid of him because he's not representative and it's going to drop things way too far out. For our self-report measures, there's only so far you can get on the top of that. So you can tap it out. It's not an infinite level to which you can separate yourself from the top of it. So a lot of the things that we're looking at sort of curve that in quite a bit, but we still just want to make sure that we've got a good justification for why we're identifying scores, these are the extreme scores, and then what we're going to do with them and sort of their potential to be able to impact results. So, yeah. If you're fine with outliers, we'll work a lot with this. It's been important semester and next working with outliers, so you get lots of practice with it. Real quick, if we're going through thinking about graphical methods, distribution graphs, bar graphs. Bar graphs are nice for presenting frequency distributions, mean levels for categorical group level data. So there's a nominal variable here. This is experimental design where we've got a couple different conditions on a continuous outcome presenting sort of mean differences. Generally wanting to have some measure of precision here in terms of either standard error bars, confidence intervals. I prefer confidence intervals. Standard error bars always look really tiny, makes your data look really good, but that's not actually something that's as useful. Confidence bars on your graphs, generally the way to go to give a reasonable communication of variability in your estimates. Histograms, we're going to use these a lot. This is nice for taking a look at the distribution scores, right? So here we've got a measure, mean, median, mode, all pretty similar in this case. We've got a standard deviation of 17. Say this is 17. So slightly standard deviation of 17. What does this mean?
That's the variability from the mean.
Yeah. So we would say about on average we would expect any randomly selected score to fall about 17 units from the mean, right? We're going to have some bigger, some smaller. Skew negative 0.36, kurtosis negative 0.79. Are we worried about this data in terms of normality issues? No, right? But I don't know how many people I have in these data. Going back to the idea of skew and kurtosis tests, if I add any reasonable number of people, this kurtosis level is certainly going to come up as statistically significant. this skew, if I got a lot of people in this is gonna come up as statistically significant. And if I'm just looking at p-value, I'm like, oh, yeah, I need to transform this. I don't need to transform this is fine, right? So looking graphically at what the distributions look like and focusing on that much more so than the significance test of your skew-kurtosis, those are functionally useless. Okay. Here on the other hand, we've got more of a skew distribution here. So we've got skew of 2.41, kurtosis of 6.28, right? So this is actually categorical data. I mean, it looks like we've measured anger from 0 to 6. It's ordinal data, categorical data at best, but if we're just looking at the distribution, we're going to say, yeah, that's problematic. Probably we might need to do something with that given the level of skew kurtosis depending on the type of analysis that we're running, right? So we'll want to go through and use our histograms to draw some conclusions there. Other thing we're going to do is we're going to be working with box plots. Who here's familiar with box plots? Knows those box plots? Chris, you love box plot? You like a good box plot?
Sometimes.
Sometimes, right? Depending on what it looks like, right? So thinking about, the nice thing about box plots, we're taking these and sort of using some median-based statistics with this. And so this starts to become important. This is standard box plot. So what we've got here is scores on some outcome before and after a manipulation. The center line in these box plots, this is your median, okay? This is your middle value, this is your center value. Okay, not the mean, the median. The bounds of your box. So the upper and lower bounds, this is going to represent the first and the third quartile. CJ, what does your first and your third quartile represent?
25th and 75th percentiles.
25th, 75th percentile. 25% of your scores fall above this line. 25% of your scores fall below this line. The box here is covering your interquartile range, right? This is your middle 50 right here, okay? So 50% of your scores are falling between here. Okay? Your whiskers, this is where things get a little bit tricky. Your whiskers can mean a couple different things. One, these are the minimum and maximum values in your distribution. Or two, these are the values falling the farthest out, but still remaining within 1.5 times the interquartile range. Okay, so if all of the values in your distribution are within 1.5 times the interquartile range of the 75th and the 75th and the 25th percentile, then these whiskers, the end of these whiskers represent the min and the max. Okay. But if you've got values that are exceeding that, right, what these whiskers will correspond to are values that are just the most extreme values that still fall within 1.5 times your interquartile range. And then what you'll see is outliers, your extreme values, going to be represented as points that fall, if they fall beyond 1.5 times the interquartile range from your first and your third quartile, those are going to be represented as individual points. In SPSS, extreme outliers are going to be indicated by an asterisk, and extreme outliers are going to be values that are 3 times the interquartile range. Okay. Now I have some problem with, I don't know, I've got the new version of SPSS uploaded and things like that. Old versions of SPSS, this is how outliers and the boundaries of your whiskers should have been derived. They weren't. So we're going to have having people using SATA getting different results than people using SPSS. SATA was right, SPSS wasn't. Not that it was anybody using SPSS's fault, because they didn't know that, I didn't know that, but I need to go through, I tried to go through and see if that's been corrected in the most recent release, but just be aware of that if you're, anybody using like an older version of SPSS?
Maybe.
Okay, maybe, all right. Well, so just keep an eye on that type of thing. So anyway, within a normal distribution, if we've got data that follow a somewhat normal distribution, we expect about 95% of the data to fall between the whiskers. Okay. Now, not all of our data will have a normal distribution, but that's sort of generally what you can expect from these types of plots. Okay? So someone tell me, we've got PANIS scores here, positive affect, and 3 or 4 different conditions. Someone tell me what they're seeing in this graph. Let's start with median values. What are you seeing in the median values here?
They're all right around the 30.
Okay, so median values are looking kind of comparable in terms of values across the different conditions. Chris, what are you seeing? What else are you seeing in here?
4 has some outliers.
Right? And how is SPSS presumably identifying these cases as outliers?
With asterisk.
Well, these ones aren't asterisks; these are just open points. So, what do the whiskers represent for conditions 1, 2, and 3?
It's the 1.5 times the inner quartile range, plus or minus.
You're on the right track.
Okay.
For these 3 conditions, what is the upper and lower bound whiskers correspond to?
The minimum and maximum value.
There you go, minimum and maximum values, because there's no point above those. So these are extending out to the minimum and maximum, right?
Yeah.
So you can have whiskers that are quite short, it's just that represents the max score, okay? And then what about when we get to condition 4, what are we seeing here? What do the whiskers correspond to in condition 4 here?
1.5 times the inner
Yeah.
quartile range, plus or minus.
Yeah, so these are, this mark and that tick represent scores, observed scores that are the most extreme but still falling within 1.5 times the inner quartile range. Any values exceeding that are being identified here by subject number and
So those aren't technically outliers, but they're outside of that.
Exactly, right? And so this is another trap. I don't sort of, SPSS identifies these as outliers, but you shouldn't just identify outliers based on sort of what pops up in your box plot, right? Outliers are going to depend on the method, the study, and things along those lines. But what we can say is these case 123 and 184 are relatively, might be considered relatively extreme scores as operationalized by the fact that they fall beyond 1.5 times the inner quartile range of the 75th and the 25th percentile here. Okay. All right. What about, in general, what do you thoughts about variability across these 3 or 4 different conditions? What do you think, CJ?
Looks like number 3 has the most variability within the middle 50%.
Mm-hmm.
But 4 has the outliers with extremes.
Yeah.
So that makes it more variable as well, so I'm not sure which is the most variable. But
Yeah. Probably I would say that these are all kind of looking fairly comparable in terms of overall variability. We can see 4 has the largest range in terms of distance covered. But if I'm looking at inner quartile range, yeah, I think you're right. 3 is probably the biggest, but it's not noticeably so. Medians are all about the same. Sort of 3 looks like it's a little bit higher. Your min and your max whiskers are all, so I don't know, but just eyeballing it, it looks like these groups are looking fairly comparable with some difference across here. I don't know, we would need to run some analysis, but this is all kind of looking pretty reasonable. What about distributions? Do these look like they're kind of normalish distributions, or these skewed distributions? Pretty normal-ish, you know. I mean, I can look at this and say, it looks like maybe some skewish here, but it doesn't look too bad, right? It looks kind of, I don't know, I can't get a good sense for distribution, but I can say it looks like we've got reasonable stuff going on either side. Okay. Questions about sort of where we're getting some of this out of this distribution here? All right. What about this one? What do you think here, Alicia, in terms of just overall shape of the distribution? What are these data strongly suggesting? A lot of variability, but in terms of shape, what are we expecting here? Yeah, a lot of positive skew. We've got people bottoming out at a score of 0, right? And so what we got, these are conditions that I think these must be my dissertation data. We're doing some physiological measurements, asking people how much they exercise in terms of hours a week, right? So people are bottoming out at 0. That's the least amount you can exercise in a week. negative exercise, of course, this week. But what we're seeing is, as you might expect with undergraduate hours of exercise per week, is a skewed distribution, right? You've got most people kind of, and again, bouncing between maybe 4 and these median values, probably aren't all that different, but in terms of extreme values, right? So each one of these upper bounds of the whisker representing the most extreme value that's still falling within 1.5 times the interquartile range of the 75th percentile. And then all of these are representing scores that are either closed or open circles, still within 1.5 times the interquartile range. These asterisks exceeding at or above 3 times the interquartile range, right? So we're seeing a much different sort of pattern here than we would other places, or with the last one. Yeah.
What happens in a report like this where the sample size of each condition is different?
It won't pick that up, right? You just kind of have to know, right? And hopefully if you've got reasonably comparable conditions, but that's also something to be thinking about, right? So this is just a straight on median-based description of your data, which can be kind of a nice way to summarize things, knowing what the different graphical features in the plot represent as a way. So we'll be using box plots and histograms a lot. Histograms are nice because you just kind of look at them and see kind of where things are at. The issue with your histograms is depending on how you decided to bin your categories, that can start making your histogram look a lot different. SPSS does a pretty good job for the most part of kind of getting a reasonable estimate of it. Stated you kind of have to tell it what you want the bins to be, but depending on how you construct that histogram, you can get a plot that looks, or a graphic that looks very, very different using the same data. One of the limitations of that, box plots are nice because these are all correspond to median-based statistics, and they're going to be consistent across those. Yeah, I can make a histogram look. Depending on my choices, I can start to make it look one way or another, so depending on my wants and needs. So that's kind of the problem. They're nice, you kind of look at it, but have to pay close attention to the binning, and so if you were to change that around, then it starts to look quite a bit different. All right, questions on box plots? Yes?
I'm having a little bit of a hard time with the, I forgot what they're called, like the boundaries, I guess.
Okay, the whiskers or the boundaries of
Yeah,
box?
the whiskers.
The whiskers.
So when would we draw them at the 1.5?
So there's a data point. Someone has a value here of about, let's say, 13, okay? And this value of, say, 13 hours a week is the most extreme score within the distribution of condition 2 that still falls within 1.5 times the interquartile range, okay? So this whisker goes out to this point because that's sort of the interquartile range here is wider than the interquartile range here. So this is going to go through, if we take one of these, 1 and then a half again above these, that's the most extreme score within this distribution that's still falling within 1.5 times the interquartile range of your 75th percentile. Once we get to, let's say 15 hours, now that's a value that's fallen beyond 1.5 times the interquartile range of this point, and so now that's being represented as a data point.
So always, if we have a point over 1.5, our maximum, or the line is going to be drawn at one below.
Yeah, at the next observed point, right? And so you can see, so this whisker could be like right there, right? That just means that this was sort of the most extreme value, and then you had a huge gap, and then we've got someone hanging out up here, right? So just wanting to go through, it's actually a very nice way to go through and plot things and kind of get a sense for where sort of gaps are at. I just want to make sure that you're solid on kind of what these are looking like. Yeah.
Would 71 on the condition 2 would that be an outlier then? Because it is 3 times the.
Yeah, I mean, sort of, and this all depends. And is it an outlier? Is a $100 million question, right? I don't know. maybe it is, maybe it isn't. It just kind of depends on how I'm defining an outlier. Probably, yeah, right? You've got someone who's talking about it. So you've got 3 people in the sample reporting that they're exercising 20 hours a week, which either means that someone may have an eating problem or they're a student athlete, right? I don't know. Or maybe they're just a fitness nut. This is kind of what they do. Or maybe they just are lying and that's they wildly overestimated the amount that they're working out. I don't know. Objectively, those are large values. So probably I'm going to go through. If I were to calculate Z-scores for those, it's probably, I don't know, like 5, or they're ridiculous scores. So those are pretty easy to call. Yeah, these are very clearly outliers, right? If we're going to do something with these data, I might want to think about like, oh, what do I want to do with them, right? But the thing is what you call an outlier may be very different than someone else calls an outlier. And so what you need to do is say, these are extreme values as defined by sort of this. Right?
My other question is, so I'm seeing like in condition 1 versus condition 2, the abstract for one of them, for example, like the 8 is there, but not for condition 2. Is it because of the min and maximum kind of thing?
Yep, because what we're doing is we're calculating sort of these distributions independently for these groups, right? So interquartile range for condition 1 is noticeably shorter than the interquartile range for this. And so if we take the interquartile range of this and we go 1.5 times the interquartile range up here, we're still sort of getting, so these are all still falling in, but this starts to fall outside. Interquartile range here is wider, and so this value would probably be an asterisk here, but it's not going to be here because it just depends on sort of the level of variability. Good questions. Other questions on this? Okay. So again, final thoughts, just general quotes. I think Hal does a nice job of sort of talking about how applied analyses isn't cut and dried facts, right? It's not, these are the steps that I follow through. This is oftentimes how we're introduced to statistical processes in our undergraduate statistics, saying, okay, these are the steps that you do, these are the pull-down menus you select. If this value is greater than this, you do this. If it's not, you do this. When you get into doctoral level stuff, you guys are, whether you want to be or not, are going to be trained as applied researchers. So we want you to know the ins and outs and be able to use and apply this stuff skillfully. Again, talking about design is very, very, very important, right? We can't divorce design from our statistical analyses. I don't have a statistical fix for your garbage design. You got to think about this on the front end, and think about like at some point in time we're going to have to. Not that no one has a garbage design. You guys all have amazing designs. I'm sorry, that's kind of shit. But if you've got serious design flaws, like, oh, is there a way we control for this? No, we can't control for that. I can't make up a control for this thing, right? So one is be very, very thoughtful and careful on the front end, having good knowledge of the background, previous research, estimates that they've found, things that have gone well and not. So being careful there. And this is our statistics. We're not their people. I'm in control of my statistical procedures and what I decide to do. I'm not being sort of dictated to by sort of whatever Z-score I get off of anything. So wanting to know sort of what my options are and how I'm going to go about and sort of address one of the billion different things that often are always wrong with running our stuff. Okay. Questions on that? All right, cool. With all that, you'll be able to go through get all the stuff that you need for that first problem set. Again, that should be, have people started on this? Okay, pretty straightforward, right? I mean, it's a couple things you want to think carefully about it, just to make sure that you're considering things. Some things can be maybe a little bit tricky in terms of some of the sampling and what we call populations and things along those lines. So just make sure you have a good handle on it, but if you have questions, touch base with us, we'll make sure that you're on the right track. All right. We're ahead of the game. We jump into normal distribution, confidence intervals, probabilities, stuff like that. We're going to work with some standardized scores. Again, this is going to be probably review for most of you, but it's surprising that you actually get into it, how tricky it can be. And so wanting to just recover this so that you're strong as sort of thinking about distributions, how we sort of find scores and what they mean, how we interpret them, going to be at the core of understanding our statistical methods. So we're going to spend some time there looking at getting probabilities, otherwise known as p-values, and then calculating and interpreting some variable estimate stuff. So last week, i.e. 5 minutes ago, 2 minutes ago, 30 seconds ago, notice that if we got means and our standard deviations, right? If we know information about that, we can start to draw some conclusions about how extreme a given score is if we know some stuff about the distribution. But knowing just a single score gives us limited information about sort of the rank, the magnitude, the probability of maybe capturing some type of score relative to other scores in the distribution. And so what we can do is we can start calculating what we call our standardized scores. This is going to give us a way to evaluate more precisely individual observations within a distribution. That standardized score is very nice because it communicates information about the location of the score, the mean of the sampling distribution, the standard deviation of any given value. And what we can start to do is we can take a look at the z-score, very efficient package, and start to make a determination on where this individual falls relative to other individuals in the distribution. And what we can start to do, if we know what the distribution of those scores are, we can start to assign probabilities to the likelihood of randomly selecting a value of this score higher based on sort of known properties or known characteristics of the underlying distribution. This starts to get at the heart of our inferential statistics. This is kind of the foundation of the whole approach. Okay. So if we're talking about IQ scores, it's hard sometimes because there are a few things that we have a good idea of the population distribution. IQ is nice. IQ is a psychological construct. It's something that we've made up. And we go through, but we have very, very good measures of this that are very, very well standardized. Those of you in class with Terry, you talk about this intensely, right? But we know that because of the way these measures are developed and scaled, we know that they have normal distribution with a mean of 100, standard deviation of 15. So this is nice in terms of an example way of thinking about our standardized scores. And what we can do if we have a nice standardized normal distribution is we can start to calculate z-scores. Okay? By definition, our z-score, just as a recap, is going to be any distribution that has a mean of 0 and a standard deviation of 1. Mean and standard deviation, so this is the defining feature of a z-distribution. Okay? Two components that are communicating stuff to us, the value. The value of your z-score is going to tell you for any individual observation how many standard deviations away from the mean this is. Okay? Thinking about things in terms of standard deviation units is going to be very, very helpful. Anybody know what else we talk about in terms of standard deviation units? One of our means-based effect sizes are d-values. These are essentially just units of standard deviation. So this group and this group is different. There's a half a standard deviation difference between this group and that group, right? Or this, so there's a 1.5 standard deviation increase from pre to post manipulation or something along these lines, right? So if we take a look at our z-scores, basically what this is, that number is just telling you how many standard deviations away from the mean that observation is. And then the sign, the plus or minus, is just telling the position relative to the mean. So if I have a score of, Chris, if I have a score of negative 1.5, what is it? It's a z-score negative 1.5. What does that tell you about that observation?
1.5 standard deviations below the mean.
Perfect, right? A lot of information right there. I know where that observation is relative to everybody else. And then once I start to get fancy, I can start to tell you how likely it is to find somebody at that level or greater or lower based on sort of known properties of our distribution, right? So here, assuming we're using a z-distribution based on our normal distribution, we can very easily say z-score 1 right here. How likely is it So if I get a z-score of 1, is that very likely? Yeah, I mean, it's above the mean. It's not my most likely score. What's my most likely score? 0, right? But it's not weird, right? Negative 0.5, same thing. So even 1. A lot of information, just very efficiently packaging information about where an individual falls, right? So I want to calculate these z-scores. Pretty easy, pretty straightforward. Formula is my observation minus the mean of the distribution over the standard deviation. So if I have a distribution with a mean of 10 and a standard deviation of 2, what's my z-score if I have an x equal to 12? 1, right? How did you do that so quickly? Yeah, it's just a standard deviation above the mean, right? It's easy and fast. What about x equal to 8? What's the z-score there? Negative 1, right? 11? 0.5. Look at that, you guys are awesome at calculating z-scores, right? What about here? So again, score, I got an x of 17, a mean of 34.6, standard deviation of 8.2. Is where your calculating devices come out. Tell me what that. Yeah, hot shots, do that one in your head. Negative 2.14? What is it?
Negative 2.14.
Negative 2.14. Okay, nice. So again, so these ones are pretty easy, straightforward to do, but going through and calculating, figuring out where this individual is. So this score here, 2.14, is that what it was? 2.14. So a little over 2 standard deviations below the mean. Now what can we infer, CJ, about a score that's falling a little over 2 standard deviations below the mean?
Pretty far away from the mean.
Pretty far away from the mean, right? Assuming we've got a normal distribution that's not a common score, it's starting to creep out there, you know. Okay. So again, as we talked about before, standardization. Almost all of our test statistics are going to follow some sort of ratio format, okay? And understanding ratios, what happens on average if we, so all things being held equal, if I increase my observed value, what does that do to my z-score? Increase.
Increases your z-score.
Makes my z-score bigger, right? Nick, if I have all things being held equal, what happens if my standard deviation increases? What does it do to my z-score? Makes my z-score go down. I mean, this sort of seems like sort of basic, sort of third grade math type of thing, but it's amazing how easily this can escape people and sort of understanding, like, oh, hey, I've wildly underestimated the variability of my sample. What is that going to have? What are the consequences of that going to be for sort of my test statistics and things like that? Helping to develop this conceptual understanding of what's going on. As soon as I start fooling around with any of this stuff, what's the impact on my outcome? Does it go up? Does it go down? Things along those lines. So if you strong on understanding sort of just basic properties of ratios, it's going to help sort of wrap your head around this stuff. So, graphing z-scores, again with your problem set 2, I'm going to have you doing some of this. Just a nice way to keep through. Again, it's easy to try and run these in your head, and a lot of times you can, but sometimes as the numbers start changing around, it can start to get hard. Again, this is a big plausibility check in terms of saying, all right, here's my normal distribution. Here's my z-score, 0, 1, 2, 3. Here's my raw scores, so where does this all fall, right? So if we've got, for my distribution has a mean of 34.6, standard deviation of 8.2. Here's my score of 17, corresponds to a z-value, negative 2.15. Hanging out down here, we're just starting to get towards the table of this distribution. People have done this before, so familiar with how to go through, set these problems up, and things along those lines. Questions on this? Okay. So, what we can do with a little bit of, who's excited about algebra? When was the last time anybody did any algebra stuff? GREs, yeah. It'll be a fun reintroduction to algebra this year. What we can do, basic algebra, is start to restructure sort of this to start to solve for other things. And you might be thinking to yourself, this seems like a waste of my time. Why do I need to be working about this? One, we can sort of go through and drive things, and one of the things that I think is my sort of general, for me personally, is I've started sort of to get into kind of nuts and bolts of how some of these test statistics are organized and things like that. What's really nice is, let's say Alicia publishes a paper but hasn't given sort of basic means or variances or things along those lines. I'm kind of aggravated because I kind of need that for my research. If I know sort of how to sort of do some basic calculations, it's easy for me to start deriving what the variance is or what the sample size is and things along those lines. It's sort of like a kind of like a logic puzzle. So this is just kind of nice for a lot of what I'm doing if I'm trying to get something from papers is reverse engineering some of their stuff to try and get the basic descriptive statistics they should have put in there in the first place, but they didn't. But I can still extract that based on sort of the stuff that they've gone through and done. So if I say the raw score for Z is, what is the raw score for Z equal to 1.96, if the mean is 73.6 and our standard deviation is 14.8, so we've got 1.96, that marker sucks. Not better. There we go. 1.96. And we know our mean is 73.6. Our variance, or standard deviation, 14.8. How do I start to solve this? Someone help me out.
Multiply the left side by 14.8.
That's right, there we go. 14.8 times 14.8. Someone tell me what that is.
29.008.
29 point what? 29.008.
008.
We'll go 01, or actually here, we'll do, I told you around the 3, so we'll do that still, so we're on the same page with stuff. 29.008 equals x minus 73.6, right? Add this. What's my x value here?
102.68.
102.6 what?
08.
08, call that 1. I'm fine with that. Okay. All right, that's my answer. What should I do with that answer? Yeah, don't know because I didn't have not a lot of context, but if I'm sort of running this, I should probably check to see if this makes sense. Right? If I go through to a value of 102.6, 73, okay, that looks about right. If I would have gotten a value that's less than 73.6, should I have been concerned? Yeah, right. My value doesn't make sense given what I know about this stuff. So being careful to go through and make sure that things are correct. All right. And so with the same type of process going through algebra, I've got a mean of 65, an x of 59, I've got a z of -2, right? I can go through and calculate my standard deviation, population of standard deviation 4, observer score of 33, has a z-score of 1.5, which is the population mean. You can go through and just start using this to go through and sort of calculate different scores and make sure I've got the various pieces and parts going on with this. Okay. Does anybody want to work through some of these? Are people kind of comfortable with sort of basic algebra stuff? It's a trick question. You don't want to be the person that got on confused about algebra. If you're confused about algebra, that's fine. Come talk to me. We'll get you squared away with stuff. Does that sound fair? Cool. All right. So, again, if we're thinking about how these are useful, right? Our z-score is telling us the exact location of our original x value within the context of larger distribution. And if we, what we can do is we can start to take standardized scores from that standardized distribution and start comparing it to other distributions, irrespective of sort of means and standard deviations, things along those lines. We can start to tell you relative position of that individual across different types of scales. okay? So we say, let's say Henry's participating in a study on personality, scores 87 on a measure of conscientiousness, 73 on a measure of extroversion. Which personality trait is more prominent in this situation? Yeah, you threw up your hands, why?
You can't really tell because you don't know.
Yeah.
About the-
I don't know anything about this, right? But if you give me the mean and standard deviation, now I can go through and calculate a standardized score and say, well, relative to the rest of the distribution, this individual is scoring higher on, Henry's scoring higher, actually higher, scoring higher on conscientiousness than conscientious, or excuse me, on extroversion and conscientiousness. What if it's on the same, what if both of these on a 0 to 100 scale? Does that help you know where who's scoring higher? No, because I don't know the variability, right? And I don't know the means, right? So even if these are on the same exact scale, I still can't give a determination on relative position, absent some additional information. Right? So Claire is interested in creating a composite quality of life variable based on scores from 3 different measures. How might Claire do this? Z-scores and then do what?
I don't know.
That's, you know what? That's fine. I like your approach. You just shout Z-scores. Standard error will be the correct
Talking
answer.
about the utility of this.
Yeah. So so I've got 3 different measures. They're all on wildly different scales, but I want to have a composite index of a composite measure of quality of life, right? I'll let you know a little secret. You know who Claire is? Claire's this guy. I'm Claire, right? If you wanted to have a measure of quality of life, I got one scale that has ranges from like -32 to 32. I've got another one that's 0 to 10. Another one's 20 to 75. Right? Can I just add those up and that's my index of quality of life? No, because that's not right. What I can do is I can calculate Z-scores for all 3 of those, just giving them relative position, and then maybe compile that in a way that sort of making sure that things are going through and comparable and stuff like that. If I just add them all up, I might as well just use the one that goes 20 to 75 because that's the one that's going to make the biggest difference in that stuff, right? So we can start to use these carefully if we're trying to go through and put together measurement scores. I'm not saying that that's a good way to measure quality of life. You should probably just get a good measure of quality of life and you don't have to worry about it, but it's a poor way to do that if you wanted to. I'll give you the citation for that paper if you like. Okay, so things that we've talked about up to this point. We've talked about Z-scores as falling along a symmetric normal distribution. Please note that standardized scores don't imply normal distribution in the distribution. Turning things into Z-scores doesn't give you a normal distribution at all. We can calculate Z-scores for anything. The only thing that a Z-score means is that you've rescaled whatever your distribution is to have a standard or a mean of 0 and a standard deviation of 1. Okay. Distribution of Z-scores, shaping the Z-score distribution going to be identical to the distribution of the raw scores. It's just a rescale. It's not going to change anything. It's not a transform. If you look at the shape of your Z-score distribution, it's going to be identical to the shape of your normal distribution. But if I've created Z-scores, the mean of that distribution is always going to be exactly 0. Standard deviation of that distribution is always going to be 1 if you've done it correctly. Okay? So if I run Z-scores, I get to take the mean of my Z-scores and it's not 0, I've done something wrong. If I look at the standard deviation of my Z-scores and it's not 1, I've done something wrong within some rounding error there, right? So again, half of my time is spent going through and checking things that I've assumed that I've screwed up. I tend to not screw it up more often than I do screw it up, but I definitely do screw it up plenty enough to sort of warrant those checks. So always go through and make sure that you're checking this stuff before you move forward with things. We do this, it's going to give us a standardized distribution. This is going to have a set mean, set standard deviation, right? So we've got our raw scores, 0, 6, 5, 2, 3, 2. We've got a mean here of 3, standard deviation of 2, score of 0, 1.5 standard deviations below the mean, Z-score 1.5. Same thing for a score of 6, score of 5, score of 2, 3, 2. These are all pretty easy, straightforward to do in our head, right? It's nice and falls out. But so what we've got here now, we've got 2 different distributions. We've got our distribution of our raw scores here, and now we've also got a distribution of z-scores. Our z-scores are just giving us more information, precise information about the location of each one of these individual observations relative to the rest of the distribution. But again, if I look at the histogram of my raw scores, the histogram of my z-scores, they're going to be identical, right? Because I didn't change the shape at all. I just changed the scaling to something that has intrinsic meaning if I know what I'm looking at. Okay. Questions on sort of z distributions, any of that stuff? Okay. So, mentioned this previously, but if we think about z-scores, this is just one form of a standardized distribution. Lots of other types of standardized distributions are out there. For those of you in assessment, going to be working with t-scores. T-score is just a standardized distribution, has a mean of 50, standard deviation of 10. Okay? IQ scores, it's a standardized distribution, mean of 100, standard deviation of 15. SAT scores, standardized distribution, mean 500, standard deviation of 100. So we can go through and create, the scale is arbitrary. Mean and scientists would have a mean of 1 billion and sort of standard deviation 10 million if I want, doesn't matter, right? It's all arbitrary, but within certain fields, certain types of standardized scales are used because it facilitates communication about sort of what's going on there. But if I want to go through and I want to transform a standardized or a raw score into some sort of alternative solution, still going to transform, I'm going to use z-scores as kind of my intermediary in here. So I'm going to take my scores, my raw scores, standardize them, transform them into z-scores, and then take those z-scores and turn that into a new, whatever the distribution of standardized scores with my specific mean standard deviation. Okay. So let's say I've got a set of exam scores, want to have a mean of 500 and a standard deviation of 100. Okay. My raw distribution of raw scores has a mean of 57, standard deviation 14. What I need to do go through is calculate the standardized scores here. So again, this is kind of what's going on for, again, in intelligence assessments, right? Like there's not a, you don't score, like the average number of points that people are scoring on an IQ test isn't 100, right? There's not 100 questions in there to do. But what we do is you take the score that people do have, transform that into a standardized score, and then use that to change it into t-scores or whatever we may be using. So we've got values of 64, 43, 57, 71. So we can go through and just set this up. Again, our mean of our distribution is 57, standard deviation 14. 64 is a half a standard deviation above the mean. So that's now a 0.5. And then we can take our new standardized score. We want to have a mean of 50 and a standard deviation of 100. Well, if I'm half a standard deviation above the mean, then it's just 550. 43, one standard deviation below the mean, z-score of -1, so I just take a standard deviation away from 500, get there. Equal to the mean, 0, score of 500, standard deviation above the mean, 1, add 100 there, 660. And what we've done is we've then taken our raw score, translated it into a alternative standardized scale that's going to mean something to other people when we go through it and communicate stuff. Okay. People kind of see sort of how we went through it and that, sort of comfortable with this type of thing. Okay. So again, if we go through and take a look at our distributions here, we've got our raw scores, our standardized scale. Here's our z-score, here's our raw score, standardized scale. So we go through and making sure things are lining up. Again, it's easy to make sort of silly errors, turn things around, and sort of make sure that something's supposed to be negative, it's positive. Again, these are plausibility checks that are always good to go through and make sure that the result that you have actually makes sense given all the things that you've gone through and collected. Okay. Comfortable with this, everything to this point. Okay, we're moving through things pretty quickly, but again, some of this, hopefully these are ideas that you've been exposed to at some point. But again, let me know if afterwards you're sort of having to struggle with figuring some stuff out. But again, the reason we're doing this is just not to have fun with math, although it is fun with math. But again, is we want to go through compiling rank position irrespective of the characteristics of your distribution. And what we can do So the ultimate goal here is if we have scores that follow some known distribution, right? We know what the properties of this distribution is. What we can start to do is we can start to assign the probability or the likelihood of pulling some score of a certain value or higher, or looking between the scores, things along those. If I am going to and I'm looking at a z-score and I'm saying, oh, I've got a z-score of say 3.3. I'm like, wow, that's a pretty extreme score, right? But it would also be nice if I could go through and pinpoint exactly what's the likelihood of obtaining a score at this level or higher, right? If I can assign a certain probability to that, that's even more information that can be very, very useful under a lot of different circumstances. And so what we can do is we can start to use distributions with known properties to start to tell you how likely it would be to identify or observe an observation having these characteristics. Okay? So again, our frequency distributions directly related to probability. Okay, frequency distribution, our graphs correspond to different proportions of the population because proportions, probabilities are different, or excuse me, not different. The opposite of that, the same. What we can do is we can start representing certain probabilities as areas under a curve or frequency of a graph. Anybody here make it like a Calc 2 in terms of sort of math stuff? No? Okay. If you're in sort of higher level calculus like Calc 2, areas under a curve, this is what the whole thing is about. It's confusing. It's one of the hardest classes I took. I started out as an engineer, so I took a bunch of math classes. And I was like, I don't know if I don't. This is fine. I don't want to do it all the time, right? But essentially what we're going to do is sort of basically, this is a conceptual version of Calc 2 real quickly. So let's say we got a population of scores, 1, 1, 2, 3, 3, 4, 4, 4, 5, 6, okay? And if I go through and I plot this out in a frequency graph, right? What I can do is I can say, if you ask me what's the probability of randomly selecting a score greater than 4? Yeah. 20%. 20%. How did you do that?
There are 10 scores and there are 2 scores that are above.
Exactly. 10 scores, 2 scores above this, right? So I've got a distribution with known properties, right? And what I can do is I can say these two, basically what I'm saying is these two are exceeding the cutoff I'm looking for, and now all of a sudden I can start to assign a probability for this. Okay? So this is pretty easy, this is pretty straightforward. This is just a sort of basic unit of 10 scores, right? Where we can use the same properties if we have some distribution, some continuous distribution, where we can't actually just count blocks, right? But it's the same phenomenon. Our normal curve that we use, so there's a sort of classic z-score normal curve. The nice thing about this is there are at least a number of natural phenomena that kind of follow this normal curve. We know that this distribution is symmetrical. Highest frequencies are occurring in the middle. Things start to get less and less likely as we go out towards the tail. And again, because it's a perfectly symmetrical distribution, mean, median, mode all lining up there right at the center. Okay? And what we know is that we understand the mathematical properties of this normal curve. And so if we can start to assign positions and points on this normal curve using our z-scores, what we can do is we can start to assign and infer specific probabilities of a score that hits this level higher or lower with this stuff. So again, 2 of 10 blocks is going to be equal to 20%, so the probability of me randomly selecting a block of for a value 5 or higher, or excuse me, greater than 4 is going to be about 20%. But with our normal curve, I can do the exact same thing, right? Given the known probability of sort of this, if I know that whatever I'm measuring is falling on a normal distribution, if I have a mean of 34.2, standard deviation of 6.8, I know I can tell exactly the probability of achieving a score of 45 or higher within the context of this distribution. So our normal distribution here, a nice normal sort of bell-shaped curve. Again, so we sort of gave rough estimates, but if we get down into sort of the specific sort of areas under the curve here, our zero value, 68.26% of scores falling within plus or minus 1 standard deviation here. 95.44% of scores falling within plus or minus 2 standard deviations. 28% sort of falling in the upper lower level tail is what we can start to do if we have something that follows this distribution, because we know the characteristics of it. We can not only say, oh yeah, this is a high score or a low score, if it's under following a normal curve, we can start to calculate specific probabilities for observing observations of this level or more extreme. Okay? So this is our function of the normal curve. We know this, so we know the characteristics. Some characteristics of curves that we don't know are more mysterious. Paranormal distribution. Who knows? This comes in and it disappears. So it's harder to work with a paranormal distribution. But a normal distribution, we have a good idea of kind of what goes on, so we can go through and calculate and know sort of where things are falling. Okay? So population of adult heights normally distributed, mean of 68, standard deviation of 6. Properties of normal distribution. So what's the probability of randomly selecting an individual at or taller than 80 inches, so 6'8". So just looking at that, knowing what we know about humans, how likely it is that we randomly select someone who's 6'8" or taller? Not very likely, right? But maybe we want to be a little bit more precise about this, right? So our question is, what's the probability of obtaining x value of x that's greater than or equal to 80? So what we can do, we can sketch a distribution. We can identify our location of x equals 80 by calculating our z-score. It's going to give us a z-score of 2, right? Standard deviation is 6, mean is 68. There's just 2 standard deviations above the mean, right? We got a z-score of 2. Then what we can do is we can determine the probability of interest here using our unit normal table. Okay? So if you guys have your, I don't know if you do you have your jump into YWeb and pull up that. I've got in the files, I've got a standard unit normal table there. Go ahead and pull that up. You see a lot of these look, there's slight variations. The one I posted there is kind of nice. I pulled this from Howell. Basically what we have here, if this is our normal distribution, we've got sort of, for any z-score here, the body of the distribution is known as the larger portion, the tail going to be the smaller portion, and what we have here, if we look at the unit normal table, our z-value, the difference between the mean and the z-score here, the proportion of the curve falling under the larger portion, the proportion of the curve in the smaller portion, and then y, you don't have to worry about that. That's the height of the height of the distribution. You can ignore that column here. Well, what we can do is we can start going through and identifying specific probabilities associated with certain z-scores using our normal table. So if we have a z-score in the example that we went through, had a z-score of 2. Okay, this person who is 6'8" corresponds, given a population mean of 68, standard deviation of 6, corresponds to a z-score of 2. What is the likelihood? What is the probability of obtaining of randomly selecting someone who's 6'8" or taller based on our z distribution here? 2.28%. How did you get that, Nick? Yeah, I derived it in my brain.
It's the smaller portion.
It's the smaller portion, all right? So just want to make sure, like, do people see where Nick's getting that value? If we go find our z-score of 2, we go through, look at the value in the tail, it's 0.0228. For this probability, it's fine to round that to 3 decimals, say 0.023, right, in terms of your probability. So there's let's say we'll call it a 2.3% chance that I randomly select someone who is 6'8" or taller based on just the normal characteristics of sort of what I know about the population. Okay. So If we say normal distribution, what's the probability of randomly selecting a z-score at or greater than 1? Alicia, can you give me that probability? Yep, 0.1587, right? So not super likely, but not so terrible, right? I like it, but that's my lottery odds. I'm pretty happy about that, right? Assuming normal distribution, probability of selecting a z-score at or less than 1.5. What do you think? Back row, Chris.
So, wait, so less than?
Less than 1.5.
93.3%.
Okay.
We're looking at the bigger part, right?
Well, no, so if we want to know the probability of selecting a z-score, oh, yes, I'm sorry, yep, you're right.
Okay, cool.
Yeah.
I have a lot more questions. I was wrong.
Yeah, you are exactly. Back row, Chris got it right, 93.3%. Yeah. You weren't looking at me, so I can't just like point Chris. You know?
No, so that's fine. I like the nickname.
All right. He's a cool kid sitting in the back row.
This is the first time.
All right. Assuming a normal distribution, proportion of the distribution contained below negative 0.5. What do you think? Curveball here.
It would be the smaller portion, right?
Yeah, it would be a small portion. So what is it?
0.305, so 30.
Put a 0.309, right? So again, we're looking at, and this is where sketching these out can start to become helpful because I'm wanting to find proportion falling below negative 0.5, and so this is where it starts to become helpful. So I say, here's negative 0.5, that's actually not, but this is what I'm looking for. So I'm still looking at the tail, using my table to go through and find the proportion falling right here. Yeah.
Oh, no, I was just
Oh,
like.
okay.
Doing a hand motion.
You were what?
I was just doing a hand motion.
Oh,
while
I
was
thought
doing-
you were just saying you're experiencing emotions. I was interested in what emotion. Excitement, right? Your whole entire life will be determined, so it qualified as before and after this moment. I'm excited to have been here for it. Okay, so getting sort of all this stuff, we're pretty comfortable with this. All right. We can also start to play around with this a little bit more. If we're saying, if we're assuming a normal distribution, what z-score separates the top 10% from the remainder of the distribution? CJ, what do you think about that?
Z-score 1.28-ish.
Yeah, 1.28, 1.29, so depending on whether or not we want to overestimate or underestimate, either one of those is probably going to be okay, right? Z-score is bound in the middle 60% of the distribution.
About 1 and -1.
About 1, -1.
I'm not looking.
Well, give me a more precise estimate.
1.3 to 1.29 and -1.29.
Okay, so we want to get the middle 60% of the distribution. How might we go through and using our table and identify that?
So 0.23 then and 0.24 and
So plus or minus 0.24, that's going to be too much, right? Again, so what we want to do here, we want to find z-scores that are going to give us, say, the middle 60% of the distribution. So based on the table there, what's our z-scores plus or minus that are going to give us the middle 60% distribution? Tomorrow you got it? 0.84, right? If we look down this table, if we say mean to z, if we say 30% on this side, 30% on that side, we end up with negative 0.84 and 0.84, right? And so this can start to be useful. Let's say you want to, you're running a study, you're trying to figure out, like, so what, I want to get people who are right here in the center, right? So what are the bounds on this measure that are going to, at least within the population, correspond to sort of the middle, like 60, the sort of center 60%, right? If I know if it's a good normed measure for the population I'm working with, I can go through and say, well, it looks like a score of about negative 84 to 84. Take those population estimates, mean standard deviation, back translate that into raw scores, and then say, okay, my inclusion criteria for this study are people sort of scoring above this, below this. That's going to get right in my center distribution right here. Again, if you've got a well-known measure with norms for population that's corresponding to what you're looking at. Right? So here with our unit normal calculations, I can take raw scores to z-scores. We can do that directly. I can take z-scores to probabilities or proportions directly. If I want to find probabilities, proportions about raw scores, that's where I'm going to have to do some work and run things through my z-scores as an intermediary to try and get solve some of these problems. Okay, so again, I don't know, these are sort of not terribly difficult problems. They can be a little bit tricky, just kind of like a little mind logic problem to go through. But what ends up happening is it can start to be kind of fun, or you can decide on whether or not it's fun, but at least functionally interesting in terms of if you've got good norm measures to start to say, okay, what's the likelihood of finding someone at this level or more, particularly those of you who are clinical people. Again, thinking about, I've got someone who's come in with a measure on like an OCD scale of this. It's much easier, so I can just report the score, and I guess anybody who uses that scale can get a sense for, oh, is this a big thing or a small thing? But if I go through and it's got good norms on it, I can say that this person falls above sort of the X percentile of this, or sort of very unlikely, given that sort of only 15% of the population would be expected to score at this level or higher, and things along those lines. We don't do this enough, but we should do it much, much more in terms of trying to communicate meaningful information to people outside of just firing off some random arbitrary score from whatever measure it is that we've set up. So in most cases, what we're going to want to do is look at some score above or below some specific X value. So we're obviously going to turn our X values into Z-scores, use the unit normal table to go through and pull up a certain probability, right? So if we say IQ score or scores, the mean of 100, standard deviation 15, what's the likelihood of randomly selecting an individual with an IQ score less than 130? So what do you think on this one? So what's a Z-score for 130?
Sorry.
No problem. So if the standard deviation is 15 and mean is 100, what is 130 corresponds to a Z-score of?
Would be about like 1-ish.
Okay, so the standard deviation is 15.
Oh, sorry.
It's sort of my actual score is I'm looking for is 130. What's my Z-score going to be here? 2. There you go. Okay, no worries. Yeah. So if I'm interested in finding, so what's the probability? What's the chances of me randomly selecting someone with an IQ of less than 130? It's going to be a Z-score of 2. So what's my probability? What's the likelihood of me grabbing somebody, randomly selecting someone with an IQ less than 130?
0.0228. or no, sorry, 0.972.
Yeah, 0.9 to almost 98% likelihood. It's going to be very, very rare for me to randomly select someone with an IQ score of 130 or greater, right? So we're just going backwards with that. A little bit trickier. Let's say highway department conducting a study measuring driving speeds on highway. Observed speed, so the mean is 59, standard deviation of 10. Distribution of speeds approximately normal. What's the proportion of cars traveling? How are we going to go through and solve this? So if I'm doing this, first thing I want to do, sometimes I get turned around in my head with things. We go through, mark this down. I'm going to say mean 59, standard deviation is 10, and I want to know number of people driving between 55 and 65 miles an hour. So what I might do is I might say Z1 is 65 minus 59 over 10. V2, I take 55 minus 59 over 10. Someone tell me what my 2Z scores are here.
Negative 0.4 and 0.6.
Negative 0.4 what?
0.4 and then the upper is 0.6.
Negative 0.40?
Yep.
Okay. And upper is 0.60?
Yep.
Okay. Sometimes I forget which one of these examples turn out to actual nice numbers and which ones are not. But okay, so we've got here, we've got Z of negative 0.40 here. We've got a Z of 0.60. How do I get that number there? What do you think?
It helps to draw it out, and oh, you did already. So we would get greater than the negative 0.4, and then the less than 0.6.
Okay, yeah, I could do that, right? So I could calculate the proportion of the distribution at this level, right? And then I could find the proportion of the tail, subtract that. I could do that. That would work. Looking at the Z table, how else could I do that?
Mean to Z.
What's that?
Find the two mean to Z.
Mean to the Z, right? So either way, going to be perfectly acceptable if we're going through and doing this. So, Nick, what is just mean to Z for 0.4?
It's 0.1554.
554. And what's mean to 0.6?
0.2257.
Right. Add those two up, what do we get?
0.3811.
0.3811. Okay. So we would say, then based on sort of this question, we would say probability of cars driving between 55 and 60 miles an hour, about 38% of cars drive falling within that range, right? So we're just using the little math creativity. So this is nice because this table has a mean to Z that sort of gets some of that. Tamara, you're absolutely right. A lot of times these don't have it, so you can use go through, use subtraction to get this, right? We can do the same thing. Proportion of cars driving between 65 and 75. This starts to get a little bit more difficult, right? Because now, not necessarily, you just have to think about it. So here's a mean, and so we're looking at, we've got 65 to 75 here, right? So now, we're going to have to go through, we're going to have to figure out Z scores for 65, Z4 scores for 75, and here, now how are we going to get this, because it's not centered on the middle of the distribution. What are we going to need to do there? Subtract, right? So we can get 65 in the tail, and then find 75 in the tail, and then that's going to give us what's left over here, right? So with some of these problems, drawing a sketch might seem like is not necessary. I still recommend you do it. It just makes it easier, make sure. And then what you can do is you can go through and make sure that whatever proportion that you get looks reasonable based on your sketch, making sure everything's falling in line with stuff. questions on this? All right. Also going through and looking at values for specific probabilities. We've got a SAT scores from a normal distribution, 500, standard deviation of 100. What's the minimum score necessary to be in the top 15% of the distribution? So we've got someone look at the standard, the unit normal table and tell me what z-score is associated with the top 15% of the distribution. What is it, Nick?
2.17.
2.17. Okay. And so what does 2.17 mean in terms of where this person is scoring relative to the rest of the distribution? Is that right? We got two. We're in agreement on 2.17. What's that?
I think that's
Yeah,
one
it's
point.
lower than that.
Okay. Oh yeah, that would be.
That'd be 1.5.
So there you go. I didn't do a plausibility, so that's way too much.
You trusted me too much.
So 15%.
You're looking at the smaller.
This more, yeah. So we've got 15%. 1 point,
Yeah.
say 1.04, right? Is that right?
Yeah.
Top 15%-ish without going over. Okay. So, Alicia, what is this, if I say the z-score corresponding to top 15% consistent with 1.04, what is this, what would be a practical interpretation of this z-score here? Who do we need to find? It's not a well-formed question, but anybody get it what I'm getting at?
There's a formula to go backwards. to get
There's a
the
formula to go backward, but
Yeah.
if I just say, this observation is consistent with a z-score of 1.04, what does that mean? What are z-score in, what's the units of our z-score?
Oh, it's one standard deviation above.
Exactly, okay. So we're looking at someone who's just a hair over a standard deviation above, right? Anytime we're talking about z-scores, we're talking about standard deviation units, right? So what we can do is we can say, well, if I know that standard deviation of this distribution is 100, I can take 100 times the number of standard deviation units, 1.04, gives me, quick math, 104 plus 500. Oops. I got 604. Okay. So some of these you can do in the head, and so the nice thing about doing is sort of thinking about things more conceptually. You can crank it all out in terms of your sort of reformulating that z-score formula if you like, and I would encourage you, some of them you'll have to do that. But it's also nice, I think, to just be thinking about this in terms of, I've got a z-score, so I would need to find a z-score that exceeds 1.0, or that at 1.04, that's just saying, I need to find a score that's 1 in 400ths of a standard deviation above the mean, and then all of that sudden that stuff starts to click into place a little bit better. Okay. Same thing. What are the ranges of values that define the middle of 80% of the SAT distribution? You can go find a z-score that captures 40% above the mean, 40% below. Find what that z-score is, and then sort of do the same thing, go through final scores and things like that. Okay. So, people comfortable with how we're going through and using this to go through and find relatively interesting information, right? Like if I got your GRE score and you want to know sort of percentile or sort of percentage of people, sort of where you find and things like that might be stressful, but maybe you don't want to do that. I don't know. I'm not in your head or know what you do with your free time. But you can very easily go through with just not that much information, going through and starting to sort of calculate this based on information provided. So why is this all important, right? This process here may seem kind of trivial, but what this is this serves as a foundation for all of our inferential statistics, okay? Because we can use distributions with known characteristics to assign probabilities of some observation, what we can do is we can go through, we've been using normal distribution at this point, but there's many other distributions, mathematical distributions where we know the very specific characteristics of this, right? And because of this, because we know, assuming the null hypothesis, assuming a mean value of 0, we can go through and calculate a t distribution. We know all the characteristics, specific characteristics of a t distribution. We know the distribution of f, we know the distribution of chi-square. And so if we know the characteristics of that distribution under a certain set of assumptions, what we can do if we get a t-value of 2.5, what we can do is we can say how likely is this, how likely would it be, how likely are we to obtain a score of 2.5, assuming that the null hypothesis is true. This turns into the foundation for all of our statistical analyses, right? I know what a chi-square with 2 degrees of freedom, what the distribution that, what the characteristics of that distribution are like. I've gone through and I've found a chi-square value of 3.4. How likely is it for me to observe data that produce a chi-square value of this magnitude or greater? This is what's going through and determining how we go through and start to create statistical inference using our traditional null hypothesis testing, okay? So being able to do this, understanding distributions, being able to work with these tables, and then understanding at a conceptual level exactly what's going on with this stuff is going to give you a super duper huge boost on understanding when we start to get into issues with test statistics and sort of t-values and f-values and things along those lines, understanding when we sort of run into problems or things along those lines, kind of what's going on, okay? So in your lifetime, how often are you going to be cranking out Z statistics by hand? Probably not a ton, unless we start thinking about FX sizes as standardized scores, right? Kind of following the same type of ratio, units of standard deviation, then the answer is hopefully all the time, right? But just understanding kind of how this process goes, how you can go through and understanding how these distributions map onto probabilities and things like that, going to be sort of nice groundwork for once we sort of next up when we get into hypothesis testing. Questions about this up to this point? We're flying through this stuff. Hopefully people just sort of reviews, sort of queuing things up. This is how statistical knowledge works. It's not like you take a class and you remember forever and always. It just gets easier to pick it up next time you go about it until you've done it enough that every time you forget it's sort of less that you forget about things. So go through what I'm going to do is we'll finish up the rest of this next Wednesday, and so that you'll have problem set 2 will be due so the following Thursday or the following Friday. So problem set 1 due not day after tomorrow, but next Friday. Then problem set 2 will be due after that. So you have plenty of time to sort of go through and work on these. Just make sure you're up to speed, get these turned in early, and yeah, you give yourself a little bit of lag time between stuff. Sound good? Awesome. Thanks, everybody.